First of all, I'd like to thank the organizers for inviting me to this wonderful location. I have to say that it's really a very comfortable and enjoyable place to be. And I've greatly enjoyed the talks, and in particular, I've greatly enjoyed needling my old friends, such as Edmund in the last talk and whatnot. That's what makes science great. Right, Edmund? Okay, so what I'd like to tell you about today is work I've done with my collaborators Yoshimasa Hidaka, Chris Cortez-Altez, Hiromichi Nishimura, and Vladimir Skokov. And at the outset, it's an example. They actually want to compute something to 3-loop order, and I thought they were nuts. What I'm going to tell you about today is computing a more limited calculation to order G cubed. And it's an example of what we're doing. We want to construct an effective theory. And so we're going to relatively high loop order. You might say, okay, what's the point? And in the end, I just want to say it turns out that sometimes in QCD, doing things carefully can really be surprising. And that's, so the moral is doing something a bit perversely can turn out to be more interesting than you would have thought. So, I'd like to introduce the term of a holonomous plasma. Holonomous just means that you have non-trivial holonomy. The thermal Wilson loop has non-trivial eigenvalues, so the Polyakov loop is less than 1. This is necessary to describe the transition region near the critical temperature. The calculation of the holonomous potential at 1-loop order was done eons ago. At 2-loop order, it was done in the early 1990s. I'll tell you some stories with that. And what I'm going to tell you about today, the punchline is we're going to calculate for weak holonomy. So G times A naught is on the order of the Debye mass. So this contributes to quantities of order G cubed that, for those of you who've computed the free energy in perturbation theory, should be well familiar with. And it turns out that in order for things to make sense, that you actually need to introduce dynamical fields in order to generate non-trivial holonomy. That's the punchline. And these dynamical fields are two-dimensional massless ghosts. And I'll explain precisely what that is.
2-loop order, whether it has been done?
Yes.
Okay.
It was first done by Enquist and Kayante, and the full calculations were done by Adrian Dumitru, Young Guo, and Chris Cortez-Altez in 2014 for an arbitrary gauge group.
Okay.
Okay. So the first half of the talk, I'm going to use slides because I want to review things that we did previously, and then I'm just going to use the blackboard. But if you go online, you'll see all details. So if some things are unclear in the second half, you should be able to understand it. So the first thing I want to emphasize is that from the lattice simulations, there's a t-squared term in the free energy, which I'll refer to as deconfined strings. And I'll explain to you why that is. I'll then review results from Polyakov loops, again from numerical simulations, which indicate a relatively broad transition region from a confined to a perturbative regime. And then results from matrix models, from effective models, which indicate a narrow transition region. Okay, so this is results by Borsani and collaborators from 2012. You know, of course, that at finite temperature, at high temperature, the pressure will be a power series in t to the 4th times powers of the log of the coupling constant, which is powers of 1 over logarithm. And what they showed, normally what you see is the energy minus 3p, which vanishes in for an ideal gas, divided by t to the 4th, and what they plotted is instead divided by t squared. So eventually at high temperatures, this is going to be dominated by the conformal anomaly, and so it will eventually go up. It goes down, this is pure gauge, at low temperatures because the pressure of glue balls is very small. But the point is that except for a transition region, about 20% around the deconfining transition temperature, this is a relatively flat quantity. This is on a log scale, but it's been confirmed for other numbers of colors, and I believe, Rashif, you did some simulations, no? Yes, for higher N. And so one way of remembering this is that in this transition region, there's a very simple formula. So you have a leading term that's t to the fourth, and it's minus t squared times the transition temperature. And this number is really very near 1 because this pressure has to get small. I'll refer to this as deconfined strings. You may object, it's like, well, it's just a t squared. But it really is if you look at this, I mean, this doesn't have to be a power series in t squared. There could be t cubed terms, there could be t terms. Besides t squared, there could be a bag constant. I'm going to use it as a motivation, but I think it's very suggestive. We certainly think that hadrons will persist in the deconfined phase. In the confined phase of a pure gauge theory, that's composed just of strings, and so these strings should persist. Now, why it's a minus sign, I can't tell you. But anyway, if you wish, you can just take it as terminology and not take it too seriously. If you look at this, you also see that in a region between the deconfining temperature and 20% above, there's something more complicated going on. Okay, this is also true in 2 + 1 dimensions. Now, you might think that, oh, well, this is just some kind of glue ball or gluon mass, so it's t to the fourth and a mass squared. If you try to fit that, in fact, this turns out to be too big. It has the right sign, but it's too big. But if you go to 2 + 1 dimensions, you would then conclude that this should be t cubed and then a term linear in t, again, if it was mass squared. Instead, again, you see a term that is proportional to t squared, and the easiest way is to say, well, the pressure has to vanish at the deconfining temperature, so it has to be t cubed minus t squared times the transition temperature. This is work done by Caselli et al. They plotted things in a different way. It's e to the minus 2p. Remember, this is 2 + 1 dimensions, divided by t cubed. And they plotted it versus 1 over t. So if it's a t squared, this should be linear. And so this goes from about 10 times the transition temperature to about 10% above. And they did it actually for 2, 3, 4, and 5 colors. So again, I will take this as evidence of some sort of deconfined strings, whatever that may mean. But it's really a very striking and unexpected feature that came exclusively from careful numerical simulations on the lattice. And for those of you who remember, the first careful studies were done by the Bielefeld group of Karsh et al. In '96, and it was hidden in their data, but they didn't plot it in this way. Okay, well, we have some sort of t squared term. The other thing we can measure is the Polyakov loop. This is an exact order parameter in the pure gauge theory. So in the pure gauge theory, I'll look at these black points. It's this is for SU3. It's non-zero, and then it drops strictly to 0. With dynamical quarks, this tends to bias one of the Z3 vacua, so it turns on smoothly at all temperatures. But the point that I want you to remember from this is that if you look at this, this is the transition temperature. The loop is, first of all, extremely small, and there's also a very broad transition temperature region and temperature. Okay, what I'm going to tell you about today is a matrix model that's based on non-trivial holonomy, which is basically just taking constant A naught. So for SU2, what you do is you simply take A naught classical proportional to the sigma 3 matrix, and then you have one parameter Q. The Polyakov loop, which is the trace of the thermal Wilson line, is then cosine of pi times Q. And what you can show is that you get a classical you have no classical potential, but you get something generated at one loop order, and I'll show you how to compute this later. What you get is you get a simple quadratic potential. And so this is where the Polyakov loop is equal to 1. This is where the Polyakov loop equals -1. And what we would think is the confined vacuum, Q equals 1/2, because then cosine vanishes, loop equals 0, is in fact a maximum. So what we want to do is construct some sort of effective model where we take this perturbative potential and we add something to it in order to make this the stable vacuum. So this is a model that I developed with Adrian Dumitru, Young Guo, Yoshimasa Hidaka, and Chris Cortez-Altes. What we do is by hand, we add a potential for this variable Q. You can generalize this to higher end, but you can get the basic point from two colors. And then what we'll have is we'll have a potential that's a sum of a perturbative term and a non-perturbative term. This you can think of as representing, integrating out whatever fluctuations you think drive confinement, whether it be dions, byons, strings, or whatnot. And what we find is, well, what you do is you find the minimum of the potential, and then the pressure is minus the value of the potential at that minimum. So it's a straightforward thing to do. What we find is that the expectation value of this quantity Q is only non-zero in a very narrow region, or only significant, between the transition temperature and about 20% above the transition temperature. The whole tail that you saw previously here is actually generated by a constant term that we add by hand. So it's this constant term, this C3, that gives rise to that plateau. And everything else going on near the transition temperature is coming from these two terms. Now, we model these terms similarly to what happens in perturbation theory. In fact, this term is identical to that which you get to one loop order in perturbation theory. But the other term is somewhat special. It's linear in Q. And we argue then that you had to add such a term in order to ensure that the holonomy turns on smoothly. Because you can think of this as some kind of Higgs model. And if you didn't have this kind of term, then you could have a first order transition between the ordinary perturbative vacuum, where Q equals 0, and a holonomous vacuum where Q is non-zero. And this is, in fact, much of what I'll talk about in the second half of the talk. Okay, so we can use this to compute Polyakov and 't Hooft loops, and I'll now show you what happens there. First of all, we have to fix the parameters. So we take, let me say as well, we assume that this term is proportional to t squared. Now, this constant term has to be proportional to t squared. These terms don't really have to be, but we just made the simplest possible ansatz and chose that. And this is fitting to lattice data from the Bielefeld group and also from Data and Gupta. And we basically, it looks like we have three parameters. In fact, we assume that the pressure is 0 at Tc and that the transition happens at this temperature Td. So we're left with only two parameters, and we can obtain a reasonably good fit to the lattice results. We could have done better, of course, by adding more parameters, but we were trying to find a model with a small number of parameters as possible. So as I said again, this parameter C3, which is just constant, this is now e to the minus 3p divided by t to the fourth as it's normally plotted. This is a 1 over t squared fall off, which is due to this constant C3, and everything else in terms of the variation is arising in this region to make the energy minus 3p turn over. But this is just an effective model, so, perhaps you shouldn't take it too seriously. In fact, the whole model is motivated by the Polyakov loop, and we have pathetic agreement with the Polyakov loop. It's really pathetic. This is the two-parameter model. Basically, it goes to 1 very quickly. That's the comment that the transition region appears to be very narrow, whereas the lattice, it's extremely broad. And this is data by Gupta, Hubner, and Kaczmarek, which I believe it's been superseded somewhat by more recent techniques with the Lucia analysis, but it hasn't changed the qualitative behavior. In any case, besides calculating the Polyakov loop, we can also calculate the 't Hooft loop. For those of you who are familiar with that, it's basically, this is the pure gauge theory, so we have an interface tension between Zn degenerate vacua, and so that's just the statement that this is one Zn vacua, that's another one. Here the loop equals 1 minus 1. So there's a tunneling problem, and we can compute this interface tension. It's a standard calculation once you realize how to do it. This is something that Bhattacharya, Tanmoy Bhattacharya, Andreas Gash, Curtis Altis, and I did some time ago. And what we've done here is apply it. This was a calculation using just the perturbative potential. Here we've done it including the non-perturbative terms. And near the critical temperature, we obtained rather good agreement with the lattice results. So the point is that if we look at the 't Hooft loop, we get very good agreement with the lattice results. If we look at the Polyakov loop, we get horrible agreement. And the conclusion I'll draw from that is I would think there's something peculiar going on with the Polyakov loop on the lattice that I don't understand, some sort of finite renormalization. You can also see this from the results with quarks. This is work that I did with Vladimir Skokov a few years ago. I'm not going to describe to you the model in detail. It's a long analysis, but I want to give you the punchline. What we did is we took a linear sigma model and we added quarks. Now, we added dynamical quarks that couple to the gauge field, so they'll also contribute to the holonomous potential, and in particular, they'll break the Z3 symmetry. In the gluon part of the potential, we kept the deconfining transition the same at 270 MeV, and then tuned the Ikawa interaction of the quarks to the sigma fields to get the correct temperature for the chiral transition of about 150 MeV. And one thing that is a very non-trivial test is the potential for the pure glue was adjusted to get things right above the deconfining temperature of 270, but we didn't really worry about what happens below. And in particular, you might worry that this term can generate a negative pressure and drive the pressure with quarks negative as well, since it's such a much lower temperature. That's not what happens. This is a plot of e to the minus 3p over t to the fourth. Once you add quarks, it does not behave like 1 over t squared. The effects of the expectation value of the Polyakov loop alter that behavior. This is the results from lattice QCD. This is the results from our chiral matrix model. So we overshoot it by 20%, but as an effective theory, we of course could have added more parameters to obtain a better fit. As in the pure glue theory, the transition, 270 is here.
Yeah, so why do you call that now as a deconfinement temperature?
No, it's just a parameter in our model. We don't call it it's just, what we did is we took this potential where this TD is 270, and then we added quarks.
So you just froze that and added.
We just froze that, yeah. In particular, if you look at susceptibilities of the Polyakov loop and the like, they agree qualitatively with the lattice results, but it's not, you don't speak of it, you can't speak of it as deconfining transition. And nothing's really happening at 270.
Rob, in your previous slide where you added the Zn interface tension, so this is an extra part which comes from your one loop calculation of the interface tension in the potential, in addition to what you added by hand, as you say, the non-perturbative part. Okay. And then you see that this is the behavior which is like sort of reproducing the results.
I mean, basically, if you just kept the perturbative result, the perturbative potential, this is what the interface tension would behave like. And this is what it behaves like when you add the non-perturbative term. Anyway, as for the gauge theory, the transition, as indicated by the Polyakov loop, is much broader than in our model. But what I want to point out is this is the second chiral susceptibility. This is chi2, this is second susceptibility with respect to baryon number. This black curve is the result from our model. It overshoots things. The red points are from the lattice, but you notice from the lattice, it's even so chi2 is near the ideal gas value already by about 250 MeV, and then it's really very flat. So if you look at quark number susceptibilities, they also suggest a relatively narrow transition region. Well, perhaps that's just an excuse because our model doesn't agree well with the Polyakov loop. Okay, before I go on, I think, let's see, okay, so this is what I'm going to talk about now. This is the new calculations. I'll first of all review what happens at one loop order, what happened at two loop order. Here, basically, if you use a gauge-dependent source, you find a gauge-dependent free energy. That's hardly a surprise. You want to use a gauge-invariant source. The result you then get to order G squared is gauge-invariant, but it's not obviously transverse, and I'll discuss that. And I'll then discuss the order G cubed term in the free energy for small holonomy. And we find a very peculiar result that the free energy for off-diagonal gluons is discontinuous as the holonomy vanishes. It's a preposterous result. It can't be right. It's just bizarre. If we generate non-trivial holonomy with dynamical fields, then everything behaves smoothly as the holonomy turns off. I'll give a particular example of massless two-dimensional ghosts, but this is an illustrative example, and I'm not arguing that it's evidence that these fields have to be there. So could you raise the screen, please? Okay, so I'm going to try to give a Blackboard talk now, because these are really great boards. It's just great boards. Okay, so first of all, I want to say, I'm sorry I wasn't here on Monday. There's very interesting work by Manada Biswal that she did with Degal and Samia. Is that how you pronounce it? Which is very similar to the things I'm talking about. So first of all I'm going to do is usual background field calculation. So I'll take an A0 classical is 2 pi t divided by the coupling times the matrix Q. This Q will be a diagonal matrix, so it'll be Q1, Q2, and so on. And it will, of course, be traceless. Okay. Now, I'm going to work in background field gauge. And this is very nice because you want to take d mu classical. What am I going to have? It's actually probably the simplest background field gauge you can ever do. So this is the adjoint derivative. And if you take I times this and go to momentum space, what you have is you have what we call colored momenta. So this is going to be, normally what do you have? You have 2 pi t times an integer n, and then because of this commutator, if this is a diagonal field, so if you have some matrix AB, well, if I act on one side, I'm going to get a QA. If I act on the other side, I'm going to get a QB. So it's basically you do everything you do normally, except you have these funny AB indices floating about. So you might think, oh, this is trivial. Come on. Jesus, you know what we heard Spirit telling us about, what was it, calculations to 5-loop order? Okay, I'm exaggerating slightly, but you know, these days people can do incredibly impressive calculations. So here, the perturbative result at 1-loop order is just -2 trace log P naught AB squared plus P squared. So this is easy to work out. This is and this result itself, so here L is the Polyakov loop in the fundamental representation. So this is classical is A naught classical times divided by T. So this is going to be e to the 2 pi IQ. And this is a matrix, remember, it's a diagonal matrix. And you might say the thermal Wilson line is a gauge variant operator. That's true, but its eigenvalues are gauge invariant, and that's what we mean to represent by these Qs. One thing you can see is that it's an infinite set of terms. And this comes because when you expand this trace, it comes from the massless field wrapping around in imaginary time an infinite number of times. It's also interesting, this 1 over n to the 4th, this 4 comes because we're in 4 space-time dimensions. If you were in 3 space-time dimensions, this would be 1 over n cubed. If you were in 2 space-time dimensions, this would be 1 over n squared. And that will be interesting for what follows. Okay, but you can work this out, and this is what you get. It's essentially the analogy of that potential that I showed earlier. There's first of all a term independent of the Qs. This is basically the pressure of an ideal gas of gluons. And then you have this x squared 1 minus x squared potential. And you have to be careful. The QAs actually are periodic variables because the only thing that enters is the exponential. In fact, they, because of the Zn symmetry, they live in what's known as the Weil chamber and the like, but you don't have to worry about that. And you can see that this term proportional to Q squared in B2 will clearly give you the Debye mass squared. Okay, so that's what you get to 1-loop order. So now let's go on to 2-loop. And this was work done by Enqvist and Kayante in 1990, and there were others who worked on it previously. And what they did is they just added a source like J naught A naught. So you would think this would be a fine thing to do, but what they find is they get a result. I'm not going to write it down, but when you calculate it, what you find is you get various things. You get a product of B2s. This is proportional to G squared. I'm not going to, but you get something that is proportional to the gauge fixing parameter. And these are the standard Bernoulli polynomials. I'll just write down the simplest one, which is, as I said, 1 over n squared. And this is, now I get to use colored chalk. I love colored chalk. And there's a term that's linear that will play an important role in what comes. But, I mean, you think, yeah.
Sorry, this x is qa minus qb. It's the difference in the... Well, this x is qa minus qb?
Oh, I'm sorry. I'm sorry. No, I've been sloppy. This is B2. This is B2 of x. This is some constant times sum of A and B, B2 QA minus QB. You always have to sum over the colors, sorry. Anyway, it's first of all gauge dependent, which doesn't make any sense. And secondly, if you actually look at this, you appear to get an expectation value for QA that's proportional to C, which appears to indicate that you spontaneously break CP, which also doesn't make any sense. So people didn't know what to make of that, and the answer was given by Belyayev in 1991, who pointed out that, well, as I mentioned before, the thermal Wilson line, which is the path-ordered exponential of Ig, integral of A naught, transforms homogeneously under a gauge transformation. So while it is gauge variant, the eigenvalues are not. And what he showed is that there's a shift in the Q's, this is for SU2, proportional to the gauge fixing parameter times G squared, and that when you take this into account, you find that the perturbative result, the two-loop order, is proportional to that at one loop order and gauge invariant. And this also entered into our analysis of the Zn interface tension at next to leading order, and was also confirmed by Dumitru Guo and Cortes Altes in 2014. There is, however, a very peculiar aspect of this, and that is that when you compute this, so to be clear, what you do now is you just take this funny colored momenta here, and you compute one-loop diagrams. So what do you compute? You compute this. You have a ghost loop, and you have this. And so this gives you a pi mu nu perturbative. And you can then compute P mu, now this is a colored momenta, pi mu, pi perturbative is color indices mu nu, and I'm suppressing some of them, but you get something non-zero. It's proportional to delta. It's only for the timeline component. It's something that's G squared T cubed, but it's proportional to a product of B3s. And I won't write down the B3s. All you really need to know is that B3 of x is the derivative, actually 4 times, of B4. So it looks like some sort of funny tadpole term. But, well, now, in fact, when Cortes Altes computed this, this was computed using a gauge variant source. To obtain this, he used gauge invariant sources such as trace eval and powers of trace eval. Since he used gauge invariant sources, it's consistent with the BRST identities. But as you might imagine, oh, and you can see that if I take p mu, p nu, if I dot both of them into it, it's still non-zero. It's a terrible problem in understanding gauge invariance, in particular for the terms of order g cubed. And I'll show that to you shortly. But it's basically you're used to things being transverse. And it's not clear why adding a background field destroys this. So this is one thing that we figured out. So what we did is we took a series of sources. We took Sj, and we took 1 over v integral d cubed x times. Now, we took actually n sources. So you might think we took one too many. For SUN, you have, because it's a traceless matrix, you have n minus 1 independent eigenvalues. We'll take n anyway. And then what we do is, well, you want the variation, the linear variation to vanish. And so what you're going to find is, well, you take a variation of this, you're going to get something like 1 over v. Well, this is what the loop's reduced to. This is the first derivative of the loop. And then you get a bunch of terms involving the B3. Summed over B equals 0. Okay? And then you can show that if you sum over A, that you get a constraint such that, oh, this is times JR. So you have a constraint that there are only n minus 1 independent sources, and that's fine. But the one thing here, what we've done is we've taken this L, this is the full L, and we've expanded to linear order in A quantum. But this L is an infinite series in A quantum. So there are terms quadratic in A quantum. And in fact, what you can show is there's a contribution to the not component. So this is simply saying I can expand. I'm going to get, if I have something here proportional to a non-zero source, I'm going to get something. And what you find is you get minus 1 over P naught AB, some number. And you get okay, and this is by using the equations of motion, and there's something actually really amazing that happens. Notice here, I didn't tell you what the J's are. From the equations of motion, I constrain this particular combination of the J's, but what happens is when you compute it to quadratic order, this particular, all this details of this totally drop out by using equations of motion. What enters into the quadratic term is the same thing that enters into the equations of motion. So in fact, this is true not only for sources that are linear in the Polyakov loops, but for sources that are in fact quadratic, and we believe in general. And you notice from this term, looks awfully like this term, and in fact what you can show is that P mu AB times the perturbative term plus the source term is equal to 0. So this total pi is transverse, which is very good. And so that was the first surprise. So now let me tell you what happens when you go to order one loop order, one loop higher. So I'll leave this here. This I don't need. So for those of you who remember how to calculate the G cubed term, it's actually very straightforward. What I'm going to do is I'm going to assume these QAs are of order G. So basically, QA times T squared is going to be on the order of the M Debye squared, where this M Debye is the normal G squared T squared term, QA squared. So the order of G squared T squared. So what we want to compute is this. And it's trace log of P mu A B squared, where this is the 4 vector, plus where these are colored momenta, and from this term, you can see that, well, if I take a variation with respect to C, what's going to happen is that this, I'm going to take P mu, P nu, and dot it into this. So if this is transverse, it's automatically going to be gauge invariant. So that's why we needed to establish something that was gauge invariant, because then we can choose Feynman gauge, and we can just compute this. So this is what I'd like to tell you about. And there are two kinds of contributions. Clearly, since we have a background field, the diagonal contributions are going to be different from the off-diagonal contributions. And the first thing you find is that the mass squared of the diagonal gluons is negative if you use sources with any finite number of loops. And basically what happens is, I'll just briefly draw for you a phase diagram. I won't be able to explain it in detail, but I think you'll get the picture. Let me take two colors. Well, okay. The point is the following. I won't draw the phase diagram. This is some number, and then remember the potential was Q squared, and then it's minus absolute value of Q cubed plus Q to the 4th. Okay? Now, assume I add any finite number of loops, like loop squared, loop to the 4th. This is two colors, so loop is cosine pi q. If I expand this about q equals 0, I'm going to get a power series in q squared. Now, I can clearly take any set of terms like this and arrange for the coefficient of the q squared term to vanish. But if I do that, I'm going to be stuck with this negative q cubed term. And what that is going to do is always drive the transition first order. So what you can show is that if you add sources here for J1 and J2, you can get to a region. What you want to do is get to a region where there's a second order transition. This is the perturbative vacuum, but instead, before you get there, you're always going to find a region of first order. Simply because of this cubic term. And this cubic term arises because it's a non-analytic about q equals 0, because it's a sum over an infinite number of loops. So what we do is we want to add a term that has an infinite number of loops. And so what we add is a term proportional, well, okay. what we add is a term that is like this B2. So we call it, it's like a two-dimensional field.
Excuse me. What is x-axis and y-axis over there?
I can't hear you.
What is x-axis and y-axis over there?
These are these sources. This is, I should have mentioned, following work by Nishimura and Ogilvy, who pointed out that you have this region of first-order transition but didn't notice this region. But the basic physical point is if you get a negative cubic term, you're always going to get a first-order transition. So we want to add a term that basically is linear in the field for small values. Oh, and this x should be the sum over QA minus QB, but presumably you get it. Okay, now if we do this, it solves a problem with the these masses being negative. Then the masses are always positive. Everything is fine for the diagonal gluons, but I'm not going to go through it for reasons of time. What you can show, and it's really kind of bizarre, that the contribution of the off-diagonal gluons is not equal to 0 if the QAs are equal to 0, and are precisely equal to 0 for any QA, even infinitesimally small, on the order of G. It's not obvious. We checked it several different ways. It's completely bizarre. We're adding a source. It's behaving linearly. It's turning on nicely, and it's just true. So what we do, and this will be the last part, is we generate a non-trivial holonomy dynamically by introducing new fields. And what we do...
So the first term is for one loop order in the potential VQ.
Could you say that?
This V here. So
this is the one loop, yes.
and
Actually, it's true to two loop order, but yeah.
Okay. And the second and third term are for higher loop orders.
No, we just add that as sources
Okay.
by hand to push it away from the perturbative.
But you said that it's up to all loop order, something like that you said.
This is true to one and two loop order.
Okay. And these are like the non-perturbative parts.
Well, or if you wish, it's like adding a source term.
So why do you do that? Like, I could not understand.
Well, we add these because I argued before you need a gauge invariant source. So the obvious thing is to add some powers of the Polyakov loop. If you don't add a gauge invariant source, you'll get a gauge variant result. So you don't want that.
Okay, thank you.
Okay, so let me tell you in the time that's remaining, well, if nothing else, you can say what we're doing is imaginative. You could use other terms. We introduce a type of two-dimensional field. We introduce a two-dimensional vector, which is x naught, which we won't change. We introduce a unit vector n squared, and we have longitudinal and transverse components. And we embed this isotropically by integrating over all directions. This is exactly like hard thermal loops, which Rebhan will talk about. And what we will do is we'll restrict the dimensions so it's like having, it's like phi lives on a sheet. So this is one of the directions is time. The other directions is along this n hat. This is 2 dimensions at short distances, and then at large distances, this field is 4 dimensions. So this is 1 over TD, which is now just a parameter. Okay, so this is actually clearly, this is made up, okay? Let me be clear. Some adjoint scalar. And what we do, so I'll just tell you, summarize the result, is we're going to calculate we're going to assume that this TD is much less than T. So we're just going to drop this, the integration over d perp squared, and we get, this is trace log of minus d hat squared. And this is going to give us a B2. And when we do this, what we find is this has to be a ghost. This is not obvious, but it turns out that's what you need, because this has to have the right sign to generate a non-zero Q, and it turns out it has to be a ghost. But when you do this, you can then compute, and what you find is that you get what I like to call a holonomous hard thermal loop. And it's just because it's 2 H's, you know, I like the alliteration. My collaborators have not approved this notation, I should say. But for example, for the longitudinal component, it just comes from taking, I should have said when you compute this F3 term, for this thing to be soft, we have P naught AB, this is P naught plus 2 pi T QA minus QB. This has to be equal to 0 for this to be soft, and the Q's are of order G. So it directly comes from taking, hard thermal loops are valid for omega on the order of GT. You take this to be I times Q, which is I 2 pi T QA minus QB. And what you find is that, for example, I'll just write down the longitudinal. It's a function of Q over the spatial momentum times arctan of P over QAB. And similarly for the transverse. And when you do this, what you can show is that if you generate the holonomy in this way, that the free energy is smoothly behaved as you turn this term off. There's some overall constant here, and as you make this constant vanish, the holonomy vanishes, and F3 is perfectly well behaved. And what we want to do with this then is use this as an effective model. We had a model calculated previously in Euclidean space-time, is use this to compute things like transport coefficients, which is certainly, again, if nothing else, imaginative. They're really ghosts. So it's easy for the model to fail. There are many transport coefficients, shear viscosity, bulk viscosity, electrical conductivity, thermal conductivity. All of these have to end up being positive. As I mentioned before, the example of the pressure is valid. That's positive. Whether or not it's true for everything else, I don't know. Let me just say in concluding Is this going to beep? Does it beep? Anyway, it beeps. Let me stop there then. Thank you. Anyway, I was just going to, okay, one last thing. Kind of like, remember Roger at the end? Like, one last thing, 10 minutes later. The shear viscosity, this is shown by Yoshimasa Hidaka and I some time ago. We showed that in Holonomous Plasma, if you compute to leading order, this is the usual perturbative result, and you find a suppression by loop squared. This will certainly be true. In this case, the question is, will the ghost screw up the overall sign? I don't think it will, but we haven't done the calculations. But in any case, look, let's be honest. I can't compete with the people on the lattice, right? They can just beat the equilibrium thermodynamics to death, right? It's at best we can do, but it's not a minor thing, is to construct an effective model that you can use to compute transport coefficients, which is much, much harder for them to compute. So that's our goal. It's the end of the day. Nobody has to ask questions. We can just go to dinner. That's fine. Because then if you ask me questions, you're going to go, are you nuts? Oh.
The perturbative propagator for calculations. But what will happen if you take all those Gribov-inspired propagators?
Oh, that's a good question. I have no idea. I mean, because I'm not really trying to construct a full non-perturbative theory. I'm just, trying to take the minimal possible model that I can compute something such as a transport coefficient. I will say, I think if you want to do something like that, I mean, other models that people take are what? Models of massive gluons. This is typically what you refer to, right? Then you have to worry about Gribov copies and all that. The problem then you run with massive gluons is how you respect gauge invariance. And what I find interesting here, we actually initially started to take things where we wanted to deal with some sort of massive field, and I just had no idea how to do that in a gauge invariant way. And for example, this surprise of what you'd think would be an incredibly technical, pointless thing of like the contribution of off-diagonal gluons to the free energy at G cubed, it turned out to be very interesting. I should say in that sense, my collaborators actually want to compute the full 3-loop calculation to G to the 4th. As I said, I thought they were demented, but perhaps you'll learn things from that as well. That's really.
Why is that something that should arise in any effective field theory?
It's our guess because I'm enamored of the t-squared term and the pressure. Perhaps I take it too seriously. As I said, though, I want to construct an effective theory, and this is the simplest example I could come up with. It doesn't mean there aren't other effective theories.
I didn't mean that way. I meant in the sense that the usual argument about writing an effective theory of Polyakov loop comes from the symmetry side. Here you are now adding something, and then in that sense, there's nothing to do with QCD.
Well, no. Here, I've chosen adjoint fields, so in the pure gauge theory, it will respect. They are adjoint. It will respect the Zn symmetry. You're asking with quarks?
No. Okay, I mean, the only thing is that you add adjoints, but nevertheless, they have nothing to do with the original Polyakov loop.
Absolutely. It's simply a way of modeling.
They are just arbitrary.
Yeah, if you wish, we had this fit for an Euclidean theory. This is a way of generating it in Minkowski spacetime. So that I'm just trying to take the minimal. I would hope it might have some deeper significance, but I can't really. That's just a
thing
hope.
I was unable to comprehend. Your first board has the reason you introduced the Q, and then you now say that the Q is of the order G.
Yeah.
That's something of an arbitrary assumption? Why did you do that?
Yeah. I'm sorry, I should have emphasized this. If this Q is on the order of 1, then except for the diagonal elements, the free energies of power theories in G squared. You don't run into any infrared divergences because these Qs will act like an infrared cutoff.
So in order to get something in G cube, you have to have Q
You
of
have to have that small. Yeah, I'm sorry, I should have explained that.
Any more questions? If no questions, we can thank the speaker then.